everyone, my name is Ioana Ciuca and I am a PhD student at MSSL UCL working with Professor Daisuke Kawata. I'm also an LSST Data Science Fellow associated with the University of Northwestern. Today I will talk to you about searching for dark matter using Gaia DR2. Just as quick disclaimer, I just arrived in London after a very long flight from Toronto, so if I make a big blunder, please let me know. All right. The outline of this talk is pretty straightforward. I will start with the motivation, and then I will go a bit into the data and the method that we've used, the results, or better said, the non-results. Don't get your hopes up. And I will conclude with implications for dark matter detection. Right, so the motivation. What do we know about dark matter? Dark matter is thought to be a cold, collisionless fluid, and the most likely scenario for it so far is that it's a WIMP particle. According to the mass and cross-section, depending on the mass and cross-section of the dark matter particle, which is a WIMP, which can be a WIMP, it can annihilate or decay into standard model particles, such as gamma ray photons. However, where can we look for such a signal? We look at, so far we want a target that is both, has a high, how can I say, there is some dark matter in it, and also we don't want to have too much bias from astrophysical sources. Therefore, dwarf spheroidal galaxies make a very good case for it. However, people have looked at trying to find dark matter in dwarf spheroidals, and there's not been a detection yet for distances larger than 20 kiloparsecs. In this particular research, what we've done, we've looked a bit indirectly. So we looked at extended unassociated gamma ray sources in Fermi-LAT data, and we asked the question, can we actually see the stellar counterpart of a dwarf galaxy there? They could be, such a dwarf could be associated with this particular source here from Bertoni et al. in 2016 shows a very extended gamma ray distribution, and we think that it may be associated with a closer, much more diffuse dwarf galaxy. We know that if we can find such a kinematically coherent structure present in the line of sight of this guy, we will not be able to say with utmost certainty that they are associated 100%, but it would be quite a smoking gun for dark matter annihilation in the sense that we can associate them. Right, so this is when Gaia DR2 comes in. We have proper motion. Right, the data and method. As my fellows back in America tell us, data is very important and we should always worry about the data. I'll go into it a bit later, but so far, what we've done, very basic stuff, we have downloaded GDR2 data for the regions of the sky associated with two Fermi-LAT sources that Bertoni et al. Thought to be unassociated extended sources, and then we also looked at 6 more. And then we've performed 7 parallax cut to just minimize the bias, and yes, we looked for kinematical signatures of a dwarf galaxy at that position. What we used, we didn't use KD. We decided to go for something more data-driven, which in this case was chosen to be an extremely convolution Gaussian mixture model, which this algorithm is a really powerful tool that aims to estimate the noise-free distribution of astrophysically relevant quantities such as proper motion. And it was introduced by Joe Bovy in 2011. What we did in this plot here, what you have on the x-axis is proper motion raw, and y-axis DEC, and then we have basically placed a mock dwarf galaxy, which we've made ourselves using codes called snapdragons and very basic Salpeter initial mass function, assuming a Plummer sphere, very basic stuff. We placed it in basically in the Galaxia background, and we tried to use SDGMM to see if we can actually recover it. I guess it's pretty obvious that we see it. It's that blob associated there. Right, cool. Next, we didn't do a very in-depth statistical analysis regarding the detectability of such dwarfs, but what we did here is that we've made dwarfs of different masses. We placed them at different distances, and we've also with different velocities. moving at different galactic velocities. And then we place them in fields, in galactic fields, and we try to see how good is XDGMM at finding these things. And then we can see from this plot that up to a distance of 20 kiloparsecs, we should be able to recover dwarf galaxies of a mass of 10 to the 4 solar masses. This, of course, is extremely conservative. And there's much more work needed to be done to lower this. However, we thought that it would be a good enough case if we find something. We didn't. Otherwise, we would have a Nobel Prize. But what we found certain kinematically coherent structures in the fields of view of these sources. One of them was this open cluster, NGC 7438. And we were able to recover the proper motion of this thing, which was a bit different than the one in literature. And we think that an improved accuracy is thanks to the amazing data we have from Gaia. We also found 2 others, but for the time constraint, I didn't put them here. All right, in this plot, just to give you an idea, first one gives you the raw data, then is basically a better resampling of the data. So it looks at this data and it comes up with basically its underlying true distribution when you've decomposed with errors. And then in the last plot, you of course have the density clusters, like how dense these things show. Right, implications for dark matter. Right, so because we didn't find anything, that was it. It was pretty heartbreaking. However, we decided to go a bit further and say, given that we didn't find anything, what can we say about dark matter? So we did what every respectable scientist should do. We looked at models. And then what we found is that for a halo, for a dwarf galaxy of a mass smaller than 10 to the 4 solar masses, at distances lower than 20 kiloparsecs, if we were to find this thing, how high should the halo mass be in order for this thing to survive? We went on and decided that based on 2 criteria, mainly on looking at classical dwarf satellites and also at simulations from Via Lactea, we found that a halo with a mass higher than 10 to the 9, pre-info halo mass higher than 10 to the 9 solar masses, that they shouldn't, if the halo mass is higher than 10 to the 9 solar masses, we wouldn't be able to find the gamma ray signal within our detectability threshold. Yeah, sorry, jet lag there. Right, okay. So now we have, armed with this upper bound on the halo pre-info halo mass of 10 to the 9 solar masses, we go further and try to calculate the flux of such a source. So yeah, up there you have the Majorana fermions, expected flux from diamond annihilation. I'm pretty sure that everyone knows the quantities in this particular equation. And don't worry about the details. What we did here is that we placed a halo like this orbiting the Milky Way. We modeled how a halo of masses lower than 10 to the 9 would lose their mass because of tidal stripping. And then in this particular plot, what you have here is the post-infall mass. Yes, post-infall mass on the right side, and on the other side is the probability distribution function of the angular scale associated with the scale, basically with the size of the halo on the sky. Right, and in what you can see is that in this model we have chosen a halo of 10 to the 7 solar masses placed at a distance of 10 kiloparsecs. We ran the simulation. We came up with these probability distribution functions after they fell. And then we see that the source, for the particular source that we considered, the angular scale is peaking around 0.5 degrees and is actually quite consistent with what we see from the models. However, the flux is for the source, observed flux from the source seems to be 2 orders of magnitude higher from what we would have expected from the models. That implies, in order to basically resolve this tension, that implies that the annihilation cross-section should be 2 orders higher than the canonical value, which is 2 to the 10 to the minus 26 centimeters cubed per second. And that is, we've done research and we know that that is not present in any of the dwarf satellites known, the classical dwarf spheroidals. It's a very large value. It shouldn't be there. We went a bit further, and then here we basically looked at how the radius angular scale and the flux would vary as a function of distance and halo mass. And again, there seems to be this tension. One explains, the other doesn't explain. But this plot, I think it would be better if I just explain this one, where we basically did the same thing, but in this particular one, we just did a joint distribution of angular scale and flux. And then in the upper side of the plot, we basically put all the observables from Fermi-LAT, where they should be placed in regards to the models. And we can see that some of them lie, in the second to sigma region. They're very close to the 10 to the 9 halo mass at a distance of 3 kiloparsecs. So we should be able to find them. But from my very, very, very limited knowledge of dark, how dark matter works, I think that the halo of that mass shouldn't survive this very close, so close to us, because you also have the tidal disruption from the disk, and also this halo would be on very eccentric orbits, so then it would lose mass. So yeah, you wouldn't be able to find it. So yeah, we have concluded that most likely the sources that we see are not due to dark matter annihilation. One day before we published the paper, we also submitted the paper, we also got this confirmation from the research from the Fermi-LAT collaboration. They agreed that the sources, the A sources that we consider are more likely to be point sources. So that was a bit of a good thing. Right. So yeah, that is it. For the next steps, I think that, in summary, basically, I think that this kind of research shows the power of using Gaia DR2 to make inference about dark matter. More analysis is done, better statistical models, better modeling, of course, but the future is bright. Although we didn't find anything, yeah. And yes, although we don't find anything, we think that work on further fields, and including higher energy signals, for example, from the CTA or something, would be interesting to look at in the future. Yeah, so that's it. Thank you very much.
Can I just remind you to wait for the microphone and identify yourself for the benefit of the...
So the problem with the dwarfs is they're all 20, 30 kiloparsecs away.
Yeah.
And the dwarfs that are nearby are precisely the disrupted structures that I was talking about.
Yes.
So have you tried correlating the positions of those disrupted structures with Fermi-LAT sources? That would be very interesting.
We haven't really, but that would be really interesting, yes.
That would be really interesting to do. These are now very close.
Yeah, we did this in like a month, so we were really hyped about doing it, but now that we've looked at it, it would be really interesting to look at that, of course, yes. Thank you. Okay, so I'm going to bed. Thank you very much.